So the next speaker is Srinivasan Arunachalam. I hope that I'm pronouncing correctly. And he will talk about simple, efficient learning of quantum many-body systems.
Thanks. Can you see my screen?
Yes, we can. But yeah, please make it full screen.
Great. 1 second. Yeah, sure. Thanks. Firstly, thanks to organizers for giving me this opportunity to give this talk, and thanks for everyone for sticking around until the end of this day. It's been pretty tiring. Right. So today I'll be talking a little bit about learning and learning Hamiltonians, and in a sample efficient way. So information theoretically can be learned quantum many-body systems. And I think most of the things I'll be talking about, I think Scott has set up the groundwork for it in some sense, but I'll tell you some more techniques that we need for our learning problem. And this is joint work with Anurag Anshu, who's at IQCN Parameter Institute, Tomataka Kuwahara, who's at Riken in Japan, and Mehdi Sulaimani Far, who's a grad student at MIT. Right, let me begin. So, the motivation of my talk is kind of like to talk of quantum machine learning. This is very hype because machine learning is awesome, quantum is awesome, like quantum machine learning is of course interesting, why not? We should kind of understand what kind of advantages quantum has for machine learning. But I think one thing that's becoming more clear in the last year or two is that getting genuine quantum speedups is not that easy. Like either you have to get quantum speedups making some assumptions which are maybe not realistic, or maybe proving like having provable separations is not so interesting. Like for a practically interesting problem is hard to prove, and so on and so forth. So it's not that easy to prove genuine quantum machine learning speedups. But kind of like just to give you like a 3-bullet summary of what kind of the works that have been going on in quantum machine learning, let me just quickly summarize these 3 bodies of work in some sense. I'm of course like omitting many works, but just to motivate my work. The first thing is like quantum algorithms for classical problems. So you just take you pick your favorite classical optimization problem, say gradient descent or linear programs or semi-definite programming. These are very well understood machine learning techniques for optimization. And we have like quantum speedups for these problems. And then you can look at something more theoretical, like you can look at computational learning theory and machine learning. And you can say, like, for example, let's just say we have the right quantum model of computational learning theory, call it quantum learning theory. You can ask, can we get quantum speedups in quantum learning theory? And indeed, in both these directions, we do have like polynomial, even exponential speedups. But yeah. And then you can have quantum algorithms for quantum problems. Like Scott kind of spoke about it right now, for example, like shadow tomography. You have an unknown quantum state. Either you want to do full tomography, or you want to learn just some aspects of the unknown quantum state. Or you could do even packed learning quantum states, which Scott introduced back in 2003. And even you could learn an unknown quantum channel. So these are all quantum objects that you would like to learn, but also I have a quantum algorithm for this. And the third thing, which I think is more interesting in some sense for maybe near term in some sense, is having classical algorithms for quantum problems. And what I mean here is like you could have like a parameterized quantum circuit, say there are lots of unknown angles in your quantum circuit, and you just can observe the input output statistics, and you kind of do classical gradient descent and just optimize the angles in your unknown quantum circuit. And this is what people have been calling quantum neural networks in these days. And you could also, like, another interesting thing, for example, let's just say you have a noisy quantum black box. Like, let's just say you built a quantum computer and it's noisy, and you would like to calibrate the noise in the unknown quantum device. Again, what you could do is you can observe the input output statistics of this noisy black box that you have, and maybe try to do some sort of classical optimization just based on input output statistics, and maybe hope to calibrate this noise or understand the noise that is happening inside this quantum black box. And again, like in all these 3 directions, we have many results in the past decade. And like many results either provide like polynomial or exponential speedups. Each one of them comes up with their own assumptions, and it's not clear which is realistic and which is not realistic. But I think if you look at 1 and 2, these are more like theoretically motivated, and you can prove theoretical results like upper bounds and lower bounds. And for 3, it's kind of slightly more heuristic in nature. It's more interesting, but it's not easy to prove results. Like standard machine learning, for example, it's just, you see it work in practice, but it's very hard to prove like formally why is it working. And in this talk, I'm going to be talking about something which falls kind of in the category between 2 and 3, and that's kind of learning quantum Hamiltonians. And this has been an extremely active area of study in the past few years. And the past few years, if you just Google like learning Hamiltonians, you'll find many papers that have looked at this. that kind of provide like clues as to why there should be a quantum way to learn Hamiltonians. Most of these are heuristic, and as far as I know, we didn't have any provable algorithm to show that you could learn Hamiltonians. And that is going to be the focus of this talk. Can you provably and efficiently learn Hamiltonians? Right, so this is like the broad motivation, and let me tell you, right off the bat, let me tell you what the problem is. So the Hamiltonian learning problem. So let H be a k-local Hamiltonian on n qubits. So if I mean by k-local, you can just think of, you can decompose H as a sum of terms, and each of these terms are nothing acting on just k qubits on a lattice. And let's say for now, I can decompose H in terms of some decomposition. Think of a poly decomposition or some decomposition of your choice, which is orthonormal. And like what I mean by decomposition is also be a k-local decomposition. So EI, think of it as like EI is a set of all poly bases, but just acting non-trivially on k sites. Okay, and let's say someone gives you copies of its Gibbs state. So what's the Gibbs state? So like, let's just say I give you let's say there's a Hamiltonian H, there's a temperature T, then rho, the Gibbs state, is like the equilibrium point at which you can represent this Hamiltonian. So that's the quantum state at this temperature T. So beta is like the inverse temperature. It's not so important for now. So you have this Hamiltonian H, and someone hands you copies of this Gibbs state. Can you learn these coefficients mu? So think of mu as like some sort of Fourier coefficients. Think of EI as like the poly basis, and think of mu as like the Fourier coefficients. Given copies of a Gibbs state of an unknown k-local Hamiltonian H, can you learn the coefficients mu up to say some error epsilon? So you know there's a decomposition, the right values are mu. Given copies of rho, can you produce mu prime such that mu and mu prime are L2 close? So let me make a few remarks about this problem. The first thing is this choice of orthonormal bases that I picked here is not so important. It doesn't affect our algorithm as such. I'm also going to assume that these interaction strengths mu or these coefficients are at most 1. And one thing that it's kind of ambiguous even in literature, like when I mean local, I mean geometrically local. So I'm just assuming that Hamiltonian is placed on a lattice and the H is geometrically local or spatially local. And beta, that is the inverse temperature for my learning algorithm, that is fixed and it is known. So I'm giving you a temperature and I'm giving you copies of this Gibbs state at this temperature. You want to find this unknown coefficients mu. And finally, for notation simplicity, at least in the first few slides, I'm just going to assume that trace of e to the minus beta h, which is called the quantum partition function, that is equal to 1. For simplicity, I'm just going to assume this for now. Right. I mean, the first question you would ask is like, why should someone even care about the Hamiltonian learning problem? Sure, it sounds interesting, but is there more reason as to why someone should look at this? And kind of, I want to give you motivation that kind of relates to like 4 branches in this information lens work. So there's a quantum motivation, there's a machine learning motivation, in CS motivation, and even like for example, there's a physics motivation. And let's just say if you have like, I mean, learning, for example, you have this unknown quantum many-body system. And let's just say you want to predict some property about the system. Let's just say conductivity or some property about the system. One way to learn these properties about the system would be to maybe learn these local interactions. So if you learn these unknown coefficients mu, you'd hope to maybe learn these local interactions, and using these local interactions, maybe you can predict some property about this quantum many-body system. So that's one reason maybe solving this Hamiltonian learning problem would help you predict properties about this unknown Hamiltonian. The second, this one is for verification of quantum systems. So recently, for example, at least in the past 3 to 4 years, there have been a lot of results on quantum SDP solvers, simulated annealing, metropolis sampling, and all of these things use this subroutine called Gibbs sampling. And I'm not going to say what this is explicitly, but let's just say you have a matrix X. These quantum SDP solvers at least assume that someone gives you like copies of the Gibbs state corresponding to this matrix X. And assuming that you have these Gibbs states, they run their quantum algorithm and obtain their quantum speedups. But we're kind of achieving near-term quantum devices, and it would be interesting. Let's just say you'd like to run a quantum SDP algorithm on a quantum near-term device, maybe even on like small number of qubits, sure. How can you be sure that someone is actually giving you the Gibbs state for the matrix of your choice? Let's say in your mind, you would like to prepare the Gibbs state for matrix M, and someone grants you copies of a Gibbs state. How can you be sure that actually you're getting Gibbs state for this matrix M? And one way to be sure is actually maybe by solving the Hamiltonian learning problem, you can be sure that your actually quantum device is preparing the right set of Gibbs states that you intended it to do. And the third thing is this machine learning motivation, which I spoke about at the start. So like our work kind of naturally generalizes a very important problem in classical machine learning, and that is the problem of learning classical Ising models. So this was something that was introduced back by Jeff Hinton back in the 80s. I'll talk more about this in a bit. But in this classical Ising model learning problem, the problem is pretty simple. You have an Ising model, you have an Ising distribution. Someone gives you samples from this Ising distribution, you want to learn the model. That's really it. And if this is not super clear now, in a couple of slides, this will become a lot more clear. And kind of, I mean, what do quantum people do? Just put quantum in front of everything. So let's say instead of an Ising model, you have a quantum Ising model, which is just a quantum Hamiltonian sim. And what's a quantum Ising? Samples from a quantum Ising distribution, those are just Gibbs states. So kind of this, you can just look at this learning classical Ising model problem, quantize it, so you have copies of a Gibbs state, and can you learn this Hamiltonian hedge, which is precisely the Hamiltonian learning problem. So this is like a natural quantum extension of something that has been looked at a lot in classical machine learning. And finally, this experimental motivation. So as I said, in the past few years, there have been many works that have kind of looked at learning Hamiltonians. Most of them have been heuristic, and it would be interesting to see if you can formally and provably show that Hamiltonian learning problem can be solved or not, and what's the complexity of it. Right, so just to recap, this is the problem. You have unknown k-local Hamiltonian hedge. You're given copies of a Gibbs state. You would like to predict the interaction strengths mu. And our main results are the following. What we show is polynomial in the number of qubits, number of samples of this Gibbs state, suffice to learn this coefficients mu up to delta error epsilon. We have to pay an exponential factor in the inverse temperature and the locality. I mean, you could maybe assume maybe even the locality is small, maybe that's fair enough, but we still have to pay a price in inverse, exponential and inverse of the temperature. And I will comment on this exponential dependence in a couple more slides again. And as I've been emphasizing, this is like the first unconditional upper bounds that one has given on the Hamiltonian learning problem. And of course, the natural question is this optimal? Like, can you do better? Maybe can you hope like poly, log, and all these parameters? So at least the unconditional bound that we can show right now is the dependence on n is kind of tight up to polynomial aspects. And we don't know what the dependence on beta plus kappa should be. So at least n over beta epsilon, that is kind of tight up to polynomial factors. Right, so this is the Hamiltonian learning problem. We show that you can do it, you can solve it in polynomial sample complexity, and we show that the polynomial in n dependence on the sample complexity is kind of tight. Right, so let me just make a few remarks which are not kind of clear in the slide. The first thing is, yeah, I mean, kind of like if you look at this problem, like you're given copies of a state rho, that's what Scott has been talking about in the previous slide. You're given copies of a state rho, and you kind of want to learn rho. So am I just solving shadow tomography under the hood? Maybe this was not necessary, but what is shadow tomography? You have a copies of E1 to EM, those are POVM elements. You have copies of a state rho. What Scott showed is if you want to predict trace of rho times E I for all I from 1 to M, only poly log in number of M, n copies of rho suffice for this learning problem. So which is already an exponential improvement in n and M. So that's like fantastic. And you would try to see if maybe you can use this for a Hamiltonian learning problem. The problem is the following, kind of, let's just say, what does shadow tomography do? It kind of predicts rho. It tells you, given copies of rho, it produces a copy rho prime. But kind of what's our goal? My goal is to actually understand what's H. I want to produce an approximation of H prime or mu prime. I don't care about approximating rho in some sense. And it's not clear how you could take an approximation of rho to get an approximation of H prime. I'll come back to this. Like this is very crucial, and I'll come back to this again in a few slides. So really, there's something more that needs to be done to go from shadow tomography to the Hamiltonian learning problem. The second question is, so far in the previous slide, I only spoke about sample complexity. That is the number of copies of the Gibbs state you need. Of course, the natural question is our algorithm time efficient? And unfortunately, no, it's highly non-time inefficient, in fact, I would say. Because kind of like our algorithm runs a convex program, which kind of computes the gradients of partition functions, the quantum partition functions, and which we know is a hard problem. But recently, there have been some works by Mehdi Soleimani-Farr and Tomotaka, and they have shown that for some class of quantum Hamiltonians, you can actually compute the partition function efficiently. And if you could do this by their work, then as a black box, you could also solve our quantum Hamiltonian learning problem in polynomial time, not only polynomial sample.
Clara. Hi, Clara.
Okay, I'm going to continue. Yeah. So, right. So that was that's time complexity, and the next statement is the one question you could ask is like, earlier I said, like kind of you would like to learn this interaction strength mu in L2 distance, but kind of if you look at classical learning, they kind of learn everything in L infinity distance. And unfortunately, we are not able to do that. All that we can do is we can reduce these coefficients mu up to L2 error small. I'll come back again to this at the end of the talk. And finally, this exponential dependence in beta and kappa, it looks bad a priori, but I think it cannot be generically avoided. So there was this recent result, I think last year, that showed that if supposing if you could learn classical Ising models in polynomial in beta, kappa, and all parameters, then it would have some unexpected complexity theoretic result. You'll show like RP is equal to NP. So you have to be exponential in one of the parameters, beta or kappa. So it could be possible that our algorithm, at least one of the exponential factors, could be improved, but not both. And finally, one thing I'd like to mention is our quantum learning algorithm is not really quantum completely. The only quantum that you need for a learning algorithm is, given copies of this Gibbs state rho, somebody needs to be able to produce trace of rho times EI. Like let's just say I specify an EI to you, you can prepare a Gibbs state for me. All I want as a learning algorithm is just tell me what is the value of trace of rho times EI, say up to additive error. I don't need you to do anything more quantum than that. Once I get these classical values in hand, I will run a classical post-processing and I will produce to you what's an approximation of this Hamiltonian. So the only quantum part is to do these trace expectation values. So kind of, it seems to me that it might be plausible to implement it, but it's highly unclear whether it is possible or not. Right, so let me begin now talking more about classical Ising models. Right, so I'm going to motivate my entire work by first talking about what classical people have done, why is it important for them, try to slowly move as to what's the quantum non-subtlety that's going on, and going to what's our main technical contribution. So as I said, like Hinton introduced this learning graphical models back in the 80s, and there was a very big interest back then in the 80s, and in the 90s and 2000s, I'm not sure what happened, but I guess in the early 2000s, like in 2010 or 11, there's been, like Guy Bressler came up with the first polynomial time algorithm for learning graphical models for bounded degree graphs. And there've been lots and lots of results in the past decade trying of improving the polynomial dependencies, improving the degree dependence, and so on and so forth. And right now we're having pretty good algorithms for learning graphical models. And let me tell you what this problem is. This problem is pretty simple, like to state. So what's an Ising model? It's just a graph on vertices and edges. So think of it as bipartite. Odd edges on one side, odd vertices on one side, even vertices on the other side. And let's just say each edge has a weight. So, and you can naturally associate a distribution to the set of vertices. And this distribution is just the standard Ising distribution. So what is it saying? Just sum over all, so A14 times X1. So the point is I'm going to assign to all vertices a plus minus 1. So X4 is going to get assigned 1 or minus 1, same with X1, X2, X3, X5. So what's a natural way to do it? For a fixed little x, just sum over A14 times X4 times X1 plus A12 times X2 times X1 and so on and so forth. And this is just the standard Ising distribution. So Aij's, which are the edge weights, are called the interaction strengths of this graph. Theta I is called the mean field vector. For the rest of this talk, I'm just going to assume that theta is 0. It's not so important for me. And finally, one thing that I omitted here is the factor z here, as z is called the classical partition function. So what is z is just it's just a factor to ensure that this actually forms a proper probability distribution. So if you put the value of z in here and you just sum over all x, this is just a standard, it's a proper distribution d. And the question that people in classical Ising model learning care about is, given samples from this Ising distribution d, where this Ising distribution just depends on these edge weights and the values associated at these vertices, can I learn these interaction strengths? So given samples from this distribution d, give me an approximation A14, A12, A23, and A25. And what they have shown, at least what the state-of-the-art results are, is for sparse or bounded degree graphs, polylog in the number of vertices. So think of a graph on n vertices, just polylog n's number of samples from this distribution and polynomial in n time suffice to produce an approximation A tilde, such that entry-wise A tilde and A are epsilon close. So in L infinity distance, you could actually approximate this interaction strengths of this unknown classical Ising model. So literally, like, this is the problem, and this is what the state-of-the-art results are. And so let me tell you what, like, most of these algorithms, they have like one crucial idea classically. And let me just tell you, I really like this idea, although it's so simple. And some of the ideas, like, if you pick a vertex I, the influence of this I only depends on its neighbors. So what I mean by that is the following. Let's just recall. So this is the standard Ising distribution. And let's just say everything in blue has been fixed. So I've fixed x4, x2, x3, and x5. And only x1 is unfixed right now. If you now go ahead and say, right, and if you go ahead and ask, what is the probability that this unfixed bit x1 is -1? And if you just do a routine calculation, you can write this in terms of this thing, where sigma is just a sigmoid function. It's not important. What's important is the probability x1 is -1 only depends on its neighbors. So if I want to understand x1, it kind of only depends on what's a14 and a12. I don't care what a23 is or what a25 is. Like, this is really the crux of what people observe. The influence of a node only depends on the edge weights of its neighbors, not on any other edge weights. Right, and now at this point, the classical learning algorithm is kind of, the idea is at least straightforward, I would think. Let me just quickly sketch what the classical learning algorithm is. So this is the algorithm of Srinivasan and Mecca back in 2017. And recall, this is the Ising distribution. Aij's are these interaction strengths that I would like to learn. And D is this distribution whose margin is given this way. No, the distribution weights are given this way. And recall, this was the observation I made in the previous slide. If you fix a node I, and if you write down this element, if you write down this expression out, it only cares about all the neighbors of I. It doesn't care about something that doesn't depend on I at all. All right, we saw this in the previous slide. So the question is, let's just say I fix the word node I now. Let's say I care about one particular node I, and I care about only learning its neighboring weights. So kind of you can rephrase this entire question as, let's say I give you samples from this distribution, because like, let's just say I fixed an I, and I restrict to just fixing that I and looking at only its neighbors. So I look at all j that are neighbors of I. And if I give you samples from this distribution, can I approximate at least the weights of the neighbors of vertex I? So I fix a vertex I, then I look at only its neighbors, and I'm given samples from the sigmoid distribution. Can I just predict the weights at its neighbors? And Srinivasan and Mecca showed that you can use the multiplicative weights method, and they said for every I, you can do this, you can learn all its neighboring edge weights, and by some lot of more ideas, they showed that you can learn all the edge weights of this Ising model using polylog in n number of samples and in time that depends on n and 2 to the degree of the graph. So for like bounded degree graphs, say degrees log n, everything is polynomial time and the sample complexity is polylog in n. And there have been some works that have shown that you can quantumly improve this classical learning algorithm by some polynomial factors. But these works don't consider the question, what happens when you have a quantum Ising model in the first place? Right, now that the classical learning problem is clear, let's go to let's just see like what changes when we move from classical lower algorithms to quantum algorithms. And so as I said, like we had a classical Ising model learning problem, we made it a quantum learning problem. You look at the classical proof, you try to see whether it works also quantumly or not. And let me rephrase the classical Ising model in a slightly more quantum friendly way. So sigma z is just a z matrix. So think of it as like a 2 by 2 matrix, which is either 1 and -1 in the diagonals and 0 in the off diagonal elements. And sigma zi is just like, think of it like acting only on the ith side, and it just acts on sigma z. And in particular, if you write down this Hamiltonian, if you write down this expression, it's a completely diagonal expression because sigma z is diagonal, everything is diagonal. So it's actually just a classical Hamiltonian. And one way you could think of making it quantum is just by adding transverse terms. So you add off diagonal elements to this matrix HC, you get H cubed, and you have these new weights. And the question is, of course, the first thing you would like to understand is the classical crux was influence of node I depends only on its neighbors. Of course, you can ask the same question quantumly. Fix a qubit I. Does the influence of qubit I only depends on its neighbors? Of course, like you have to be more careful about what influence means now. And let me rephrase that in a more mathematical framework. Right, so let's just say you fix a vertex I, and you look at B is the set of all neighbors of I, and C is a set of all nodes, which are neither I or the neighbors of I. So what classical people observed is the fact is, if you fix B, that is all the neighbors of I that shield I, then the mutual information between I and C is 0. Like this is really the observation that they made to say like the influence of I depends only on its neighbors. All that's in the purple does not affect what's in blue at all. And for quantumly, the question would be like, can you also show that the quantum mutual information of the quantum Gibbs state of I with respect to C conditioned on B, is it 0 or not? And if this were true, at least the first thing would be just apply Kleinman's and Mecca algorithm, and you would think like, if the key idea works through, maybe even the quantum learning algorithm works through. But this is not true. So just proving this inequality for the Gibbs state is like a long-standing open question in quantum information theory. It's called the quantum CMI conjecture, and it's not clear whether it's true. Well, okay. In its exact statement, in its exact form, we know it's false. But what we know is it's believed to be approximately true. And this is what Aram kind of mentioned in his talk as well. We believe this statement is true, but with 0 being replaced by some sort of distance between I and C. So we believe it to be approximately true, but it's in its exact form, this statement is false. Right, but even in its approximate form, we don't know whether it's true or not. And that's a big open question. It's called the quantum CMI conjecture. And even if you assume it is true, if you assume the quantum CMI conjecture is true, because of this distance, because this is not 0 and because it depends on the distance now, it's not clear whether you can recover the algorithm of Kleinman's and Mecca, even if you have this quantum mutual information statement to be true. Right, so okay, fine. The main classical idea didn't go through, so you require some more quantum ideas, and that's where we are. Now I'm going to slowly start talking about what are our contributions actually. So for the entire talk, I'm going to keep this box, the running box, like given copies of a Gibbs state, and the Hamiltonian has this decomposition, and your goal is to learn this interaction strength mu. So you can just keep recalling this. Right, and the first idea that we have is this idea of sufficient statistics that is actually used a lot in machine learning. And the point is the following. Let's just say for this, I am given this copies of this Gibbs state, and let's just say I can prepare all these little EIs. Let's say not prepare. I know the value of little EIs that are just like the trace expectation of capital EI times rho mu. And let's just say I even have approximations of this. Then the first question is, okay, fine. Why can't, given these things like what I hinted before, why can't you just use like shadow tomography? Why can't you use the result of Scott or HKP or CW, which show that given just the trace expectation values for an unknown quantum state, you can kind of approximate rho. And as I said, these works kind of produce an approximate of rho mu, they produce a rho prime. And it's not even clear whether this rho prime is a Gibbs state. So it's not even clear whether this rho prime is of the form e to the minus b h prime. It could just be an arbitrary quantum state. And from this, it's unclear how you would recover in a mu or an approximation of mu or anything of that sort. But there is still something more you could do. And the first observation is the following. Let's say instead of let's just say I have objective 1, and I don't use shadow tomography now, but I'm going to use a different optimization procedure where I'm just going to maximize over all possible Gibbs states, like all possible lambdas. So H has this decomposition and all possible rho lambdas, such that rho lambda EI and rho mu EI agree. So suppose someone gives me values of little EI, and I just maximize over all possible Gibbs states that agree with this little EI. Then it's not hard to show that actually rho lambda is equal to rho mu, which implies lambda is equal to mu. So great, now we actually have some idea of how to maybe recover mu. Just maximize over all possible Gibbs states, ensure that the trace expectations between trace rho lambda EI and trace rho mu EI agree, then the Gibbs state that you output, that you obtain by this maximization procedure is exactly mu that you have been caring about. But there are two subtleties here. The first subtlety is, how are you even going to optimize over all possible Gibbs states? Isn't there infinite many of them in some sense? Because you have to maximize over all possible lambdas and so on and so forth. So there is this nice idea called maximum entropy principle. So it kind of says observation 1 can be cast into a nice, beautiful optimization problem. So let me just define this optimization problem, and then I'll tell you why it's interesting. Let's just say instead of maximizing over all possible Gibbs states, let's maximize over all possible quantum states. So it's just a PSD state with trace equal to 1. And all I say is trace of sigma times EI like the trace expectations between sigma and this unknown Gibbs state agree. So EI, which was this, agrees with trace of sigma EI. That's my constraint. And the objective I would like to maximize is the entropy of this quantum state. So the entropy is just the quantum entropy. So the question is, okay, fine, you could do this optimization problem 1, but what does it have to do anything to do with rho mu and so on and so forth? So what's the beautiful observation is the fact is if you solve optimization problem 1, it's maximized exactly for rho mu. So if you solve 1, the maximum entropy state that agrees with the trace expectation values is exactly your Gibbs state. Great, so at least one problem is solved. We at least have a kind of like an algorithmic way to go from observation 1. It's 2 is like more an SDP and it's kind of algorithmic. But the question still is there's one more subtlety and I'm going to get to that. Right, so on the previous slide, what we saw is this maximum entropy principle that says if I can produce maximize over all states sigma that has matching marginals with rho mu and sigma has a maximum entropy among the state of all states, then it equals to the Gibbs state that I care about. But unfortunately, kind of in the previous slide, I mean, if you recall, we didn't have EIs explicitly. We had only additive approximation EIs. Like, I mean, in the lab, you can't expect to produce exact expectation values. You only are going to get additive expectation values. So little EI was this quantity, and we only have additive approximation little EI prime that are epsilon close to little EI. Right, so this was the optimization problem that I wanted to solve in my previous slide. And as I said, because I don't have little EIs, I only have approximations, so I'm going to be solving this optimization problem. Right, and now the question is, okay, let's just say, for example, like rho mu maximizes this thing, and I've shown that rho mu is exactly the Gibbs state that I care about. But unfortunately, I don't have EI in my hand. I only have EI prime in my hand, so I can only produce a rho mu prime, which maximizes the second inequality, second optimization problem. Then by trivial Pinsker inequality, you can just say like, what's the trace distance between rho mu and rho mu prime? And this is just at most m times epsilon. This is not great because it depends on the number of qubits and so on and so forth, but at least it is some bound. Like in the previous slide, we didn't have any bound on how we can produce mu and mu prime, but at least now we know we can produce a state rho mu. Like shadow tomography just produces a state, but now we are saying we can produce a Gibbs state that at least is somewhat close to rho mu prime. But okay, fine. The next question is, of course, now we have this, some approximation. Can we kind of, from here, produce a mu prime that is close to mu? Recall, the goal is to approximate mu, not to produce an approximation of rho mu to rho mu prime. So we have this, can we produce mu? And this is where the main issue is actually. So kind of think of like, okay, rho mu is nothing but e to the minus beta h, and h kind of depends linearly on mu. So we know rho mu is close to rho mu prime. Let's just take the log of it in some way. Let's just take the log of it. And somehow that means kind of log of rho mu would be close to mu. Log of rho mu prime would be close to mu prime. And kind of the hope would be to say, okay, if this is true, then this is small as well. But unfortunately, this quantity, it could be exponentially worse than this quantity. And that's just because the log function is highly non-Lipschitz around 0. So once you go around 0, like the log function difference could be exponentially far, although on the x-axis you're very close, in the y-axis you could be very far away from one another. So just having this trace norm condition does not allow you to produce a mu prime that is close to mu. So we are still not done yet. So this is like the main issue here. The non-Lipschitzness of the log function kind of doesn't allow you to go from approximating rho mu to rho mu prime to actually produce a mu prime that is close to mu. Great, and so like this is where this is our main contribution in some sense. So the idea that we had is to kind of like use the idea of strong convexity, and I'll tell you what that is in the rest of the slide. So again, recall the goal was kind of I want to handle. I could produce a rho mu prime, but the point is it was very unclear how far rho mu prime is close to mu prime is close to mu, assuming I'm given this. So how do we handle this quantity? And so one way to do that is just to take the dual of the optimization problem. Right, so we had this standard optimization problem, which was the maximum entropy principle. You look at its dual, you're going to get this optimization problem, which now depends on the log of the partition function. So recall Z beta is like the partition function of this inverse temperature inverse temperature 1 beta, which is 1 over t. And H was Hamiltonian, whose coefficients are lambda i's. So you have this optimization problem, look at its dual, great. But as I said, of course, we don't have EIs, we only have approximation of EIs. So we have, instead of this optimization problem, we have this optimization problem. And you could look at the dual of this optimization problem, you have this dual optimization problem. And of course, the question is, how far could mu, the quantity you care about, be from mu prime, assuming that EI is epsilon close to EI prime. And right, and the crucial idea that we have here is kind of to use this idea of strong convexity. So kind of strong convexity puts a bound on how, so like, firstly, strong convexity is something people in like stochastic optimization have kind of developed, and it's been used a lot in machine learning. And what it kind of does is it kind of puts a bound on how slow a function changes. So in particular, let's just say you have a function f, and you look at its Hessian, and let's just say all the eigenvalues of the Hessian are at least alpha. Then you can show this complicated looking expression. Like, you don't need to understand this, but maybe the way you should think about it is think of nu as being mu and nu prime as being mu prime. Kind of what it tells you is I can give an upper bound on mu and mu prime, assuming all these quantities on the left are small. So if, supposing miraculously I can ensure that all these quantities on the left are small, then I could say that mu and mu prime are actually close. And you should think of f as actually the log of the partition function. So like, this is going to be my objective function, which I'm going to be showing is strongly convex. So, and if you look at the second derivative with respect to lambda, this term collapses, so we only have this term. So we have the log of the partition function, look at its Hessian. If you can show that it's strongly convex, then you can show that the objective, that is mu and mu prime, are actually close in L2 distance. And I mean, running ahead a bit also, this is why we kind of can only handle L2 distance between mu and mu prime. Right, so let me, because so this is the problem. So kind of what we have done so far, we have kind of reduced the problem of given copies of a Gibbs state, approximate mu. What we kind of said is like, you could have solved this primal optimization problem, but unfortunately you have only errors. But because of these errors, you can't do much. So what you do is look at the dual. And once you look at the dual, and if you can show that the objective of the dual is strongly convex, you are in some sort of good shape. So we kind of reduced the learning problem to proving the strong convexity of the logarithm of the quantum partition function. In particular, what we want to show is if you look at the Hessian of the log of the partition function, it is at least alpha. All the eigenvalues are at least alpha. And if we could show this, then we know that mu is close to mu prime, and we are kind of done. Like, this is our quantum learning algorithm. And of course, the first question is this even true for classical partition functions? Do we know that the Hessian of the log of the classical partition function is alpha strongly convex? And indeed, people have shown this a few years back. They've shown that with alpha is equal to e to the minus beta, it is strongly convex. And this kind of gives another way to obtain a learning algorithm whose sample complexity scales as m times e to the beta. And the main technical contribution in this work is we have shown that if H is a k-local Hamiltonian, let's write H in terms of this Pauli decomposition, and you fix an inverse temperature beta, then if you look at the Hessian of the log of the quantum partition function, it is actually also strongly convex with a parameter e to the minus beta divided by m. So like, this is really the most technical part of this work, took up the bulk of the work, and I wouldn't be going into the proof of this, but this is like, I've heard that this statement at least has a lot of implications in other fields like thermodynamics and other quantum many-body system questions, but for our problem, like, this was mainly used for obtaining a good learning algorithm. Because if we have this, then we kind of approximate mu to mu prime, which was exactly what we care about. Right, let me just put everything together. So what's our learning algorithm? Is the following. So recall, like, you're given copies of the quantum Gibbs state, and this H is a k-local Hamiltonian, and right, then you want to approximate mu. So, right, the first thing is you're going to use this algorithm of HKP of CW. You could also use shadow tomography, but as Scott said, like, HKP kind of is more useful when you talk about like local measurements. So you obtain all these EI primes, which are like delta approximations of these actual trace expectations. Then we look at this idea of sufficient statistics. So we solve this optimization problem. But unfortunately, we only get like delta approximations of EIs. So instead of mu, we're going to get mu prime. But what we observed is, if you look at the objective and if you show that it's alpha strongly convex, you can show that mu minus mu prime is close to e minus e prime. And right, just by some Cauchy-Schwarz, you can show this is true. It's nothing happening here. And this is where the bulk of the work goes to show that log of the quantum partition function is at least e to the minus beta divided by m. It's this strongly convex. Like again, like so the most technical work goes in part 4. Like 1, 2, 3 are kind of like well known. And if you fix some parameters here and there, the complexity of algorithm only goes in like step 1. And step 1, the complexity of step 1 is just 2 to the kappa divided by delta squared, where kappa is the locality of this Hamiltonian hedge. And if you plug in this kappa, if you plug in this delta, which I fixed here because of my strong convexity bounds, you get the sample complexity upper bound. Right. Yeah, I think I'm running out of time, so I'm not going to go to the lower bound proof. But the lower bound proof is actually pretty simple. It's much more simpler than upper bound proof. We just reduce it to some form of state discrimination and show that kind of you need polynomial in n sample complexity. And for beta and kappa, we don't even have a conditional result. So let me quickly conclude. Right, so we looked at this Hamiltonian learning problem. Given copies of a Gibbs state, can you learn a Hamiltonian? What we showed is for constant temperature and error and everything like that, everything being constant, polynomial in n, many samples of this Gibbs state suffice, and this is polynomially tight as well. So of course, there's some, well, the first natural open question is, can we tighten this gap between upper and lower bounds? The second thing is, can we make it time efficient? As I said, like our algorithm is non-time efficient because we talk about generic Hamiltonians, like generic k-local Hamiltonians, but you could look at maybe a subset of Hamiltonians which are of interest in practice and maybe see for that, can we make our algorithm time efficient, or maybe even commuting Hamiltonians. So as I said in the start of this talk, one of the motivation for this work is, can you do verification of quantum algorithms? And for that, you don't need to, like, what I mean by verification, you don't need to learn this Gibbs state altogether. You just need to verify whether this Gibbs state corresponds to this matrix M or not. So can we just test if this Gibbs state comes from this matrix X? You don't need to learn this Gibbs state altogether. So what's the complexity of testing whether it's a Gibbs state or not for this matrix M of your choice? So one more thing is, in this work, we kind of only can approximate mu up to L2 distance. The question is, and that takes sample complexity polynomial in n. But the question is, can we even approximate mu in L infinity distance? And the question is, can we do this in poly log n sample complexity? And this is known to be true classically. So classically, if you want to get an L infinity approximation, you can do it in poly log sample complexity. That's this work of Cliven's Mecca and follow-up works. But the question is, because we use the strong convexity approach, we can only do an L2 approximation. I think it'd be very interesting to see if we can do an L infinity approximation. Right, like I think one of the motivation of this work is kind of like, this is something that you can kind of try to implement. This is something that's important maybe in practice. You have this unknown Hamiltonian that's being built by a quantum black box. You want to test it, you want to learn it. As I said, there have been many works that have kind of gone in this direction, and ours kind of is the first to prove of theoretical guarantees on this work. But of course, like, we are very far away from actually achieving what people care about in some sense. So it's interesting to see what maybe experimenters really care about. Is there maybe a noisy learning model that they maybe care about? And I think pursuing those directions are very interesting. With that, I thank you for your attention.
Okay, thank you, Srinivasan. Anybody who's not muted can clap.